Welcome to the course on FPGA based signal processing systems. Today we'll be doing general discrete signal processing networks. In that network, a generalized DSP network. This is a discrete signal processing network which has the two cascaded connections. That is, one is this comb filter fully, and then other one is the recursive part here. And apart from this recursive part, we have this feed forward path as well, as we had look into this filters in the IAR filters. If you recall, the output y of n can be obtained. So these networks which can be fit into the system, which has coefficients a0, b0, a1, b1, a2, b2, and one more coefficient which is c1, and the comb filter zeros can be rotated with respect to the c1. So this structure, using these coefficients of second order, how many such DSP networks, this DSP I mean here is not digital, it is a discrete signal processing network. How many such networks can be formed? For example, here this transfer function is given. From that network we get this h of z, which is y of z by xz, has the 1 minus c1 z power minus n, which is corresponding to the comb filter with n zeros, and the rest of the thing, this is giving the numerator polynomial or denominator polynomial of the recursive network, as well as the feed forward coefficients, feed forward and feedback coefficients order 2 here. So this general transfer function can result in many of the DSP networks, which are one follows, that is, moving averager is one, computing the average of the signal, and the differencer is another network, and then integrator can also be formed from this. Leaky integrator is very well applicable to many of the integrating applications in real time. So we use we can form from this network discrete network leaky integrator. And delay network, how to introduce a delay to a signal, so that can be formed. Here I deal only with first order, it can be extended to second order and third order as well, depends on the application. And the sixth one is the Goertzel network, also, which is very much useful to extract a single tone, a particular frequency. And sliding DFT network, which is already we are familiar with that we had done a separate lecture on sliding DFT as well as a as the recursive equation of the DFT. So these 7 networks we will see one by one. From that network, what are its characteristics, how this can be used in this signal processing. So the 8th one is real oscillator and quadrature oscillator also can be formed, and comb filter, IIR filter of first order, equalizer, cascaded integrated comb, a complex frequency sampling filter, that is FSF of complex in nature, and DC bias removal. This set I will do it in the coming lecture, but first 7 we will be doing in this lecture. So the moving averager, first we take the transfer function, which the generalized transfer function here, h of z is this. So the coefficients I have shown you in the case of the general network, wherein a0, a1, a2, b0, b1, b2, c1, and what is n to be taken in this case. So we have just simulated in the Simulink. So later we will convert this Simulink diagrams into DSP builder in the Altera, or it can be also converted into the system generator case of the Xilinx. So any one of this can be done. So if you are familiar with Simulink, just browse this, how to code this, how to make this block connecting these blocks and all those things. So it can be made in the MATLAB Simulink. So I have shown you the picture of this MATLAB Simulink block diagram, wherein the coefficients are fixed this way. The C1 is here. Okay, a naught of this first coefficient, a1 and a2, okay, and then b naught, b1, and then b2. Okay, so these are the coefficients placed over there, and we can see these coefficients. We have taken n equal to 64. What is the moving average transfer function? By applying all these coefficients to this network transfer function, that h of z equal to 1 by n, because this c1 it's going to be this here 1. Okay, so we get 1 minus z power minus n by 1 minus z power minus 1. So you have n zeros on the unit circle and 1 pole on the unit circle. So it is averaged by the n number of samples which is considered in the window here. So from this case, this is the case x of n minus x of n minus n into the coefficient c1, and we have this a naught coefficient also, and then delay it once, so which is and then delay it again, so have this way to get b0 b1 b2 multiplied, this is giving the forward path. Yeah, and then we have here this feedback path which is going to a1, and then a2 also is getting the feedback path here. So it is perfectly fitting to the network which is shown, the generalized network. So from this, what is the output outcome of this moving averager? So we have taken a signal in which the x of n, we can assume this is a sample. Okay, so I have shown it with the discrete sequence here. In this, x of n is having the DC of 1 by 2.5, and he had taken sine 2 pi 50 n 50 hertz and of my amplitude 1 plus the second harmonic of amplitude 0.5. So it can be of any signal with noisy and other sensing. So the moving averager, what does it do here? So it is just extracting the DC from this. You can see this is the input signal, and this is the one y of n we got from this. This is the output which we get the sequence here. So you have this 0.5 getting extracted from this signal, which is the DC over here. So moving averages, I will take the n samples and average out and get the average values. So here we have this for one cycle at least it won't be giving the proper output, as we have seen in the case of a sliding DFT as well. It has transient response of n minus 1 samples, 0 to n minus 1 sample. So after this, for nth sample onwards, we can get the output properly. So moving averager is also called the k equal to 0th bin of the sliding DFT. So we can extract the DC from this, the signal which has fundamental and second harmonic and DC. So it's just computing the average of the signal n samples. Now the characteristics, if we take frequency response of that, before getting into the frequency response, let's see the pole zero diagram. So here the pole zero diagram is plotted for n equal to 8, whereas we have chosen n equal to 64 to get the smooth waveform here, that is per cycle 64 samples have been considered. For plotting here 64 will be too clumsy over here to show the 64 zeros, so it is for clarity it is taken n equal to 8. So we can have the zeros placed on the unit circle in equidistance. You can see 1, 2, 3, 4, 5, 6, 7, 8. And then the pole, which is here 1 minus z power minus 1, and in the denominator of the moving averager cancels this 0 and extract only DC from this. So that's how you have the timing sequence output, which gives only DC from that, and the fundamental is removed and second harmonic is removed from the input signal. So if we take this frequency response, which is from here 1, 10 and 100, it is shown over here, the frequency scale in hertz. So it is tuned to 50 hertz, that is the FS is adjusted in such a way that it is 50. So we have this 50 for fundamental and DC here. So you can have this from 1 up to 10, 20, 30, 40, 50 here. So this is considered to be, this is the fundamental one. So second harmonic is here. Okay, so it very well rejects this. The frequency response shows that the 50 and 100 and then 150 and other things will be rejected from here. So it would pass with an attenuation, DC would be here, that is, and then the attenuation will be if it is more than 10, 20, 30 and so on, the attenuation can be shown over here. So the phase shift here it's 0 radians in the here, there is no phase shift introduced in that case for this particular frequencies. So it can be tuned to get only DC. Okay, so DC it will be perfect here, that it is giving 1, it's not plotted from 0, cannot be. So the thing is we have the thing frequency DC can be extracted from this using the moving, it just averages the number of samples. And if we come to the second network, in which the differencer, taking the generalized network, DSP network, in which we substitute the coefficients as this. So a naught 1, and here this is 1, and this is 0, and a2 is 0, a1 a2 are zeros, and then b naught is 1, and then b1 is minus 1. So we have b2 0, and the c1 is also 0. So there is no comb filter part involved in this. So in that case, you get the simple differencer is h of z equal to 1 minus z power minus 1. So the network, we have kept the common network and then made this coefficients as per the requirement. The b1 is minus 1, and b naught is 1, and here b2 0, a naught is 1, and a1 0, a2 0, and then c1 0. So all other things are 0. Here this n is not there, so we made it this becomes 0. Here we get the transfer function 1 minus z minus 1. This is a differencer. So it's x of n minus x of n minus 1. So it takes the difference between the two samples. So to demonstrate the characteristics, we had this amplitude. We had taken this step input, okay, and then given the one sample difference, you can get the impulse from the differencer. Okay, so this is what is shown. This is in x of n, and this is y of n. The differencer gives the, if you give step, it would be an impulse for the differencer output. And if you take the frequency response, yeah, here the pole 0 configuration, because it has only one 0, so this one. So this is at the origin, I think, because if you write it 1 by z minus 1, so take z minus 1 by z, so that is representing this pole. It has nothing to do with this particular 0 is the differencer 0. So if we take the frequency response of it, it is plotting from 0 actually. So it is 0.001 and 0.01, 0.1, and this is corresponding to 0.2, 0.3, 0.4, 0.5. Okay, so wherein this fs by 2. Okay, so whatever the sampling frequency you choose, fs by 2, so it is increasing here the slope of the differencer, and you can have this also from you can see the change in the phase response. So the 0 at this point, which is function as a differencer in this case. So this is corresponding to it will move, it will be 0 to 0.5. Okay, so which is shown the positive frequency scale only in the frequency response. That's a magnitude response. Such magnitude and phase can be seen over here. So differencer, fine, and then integrator from the same network, the network which has h of z, the generalized network, in which for the integrator, what are the coefficients to be substituted? A naught it's equal to 1. Okay, this is 1 over here. B naught is 1, again B naught is 1. Okay, and then B1 it's going to be 0, B1 is 0, A1 again 1. So if we have this, so what we get here is 1 by 1 minus z power minus 1. This is an integrator. So this integrator, the other coefficients are made 0 here. So we have given the step input in this. So let's see the output here. So the step input is of 1, and it keep integrating for a value of, as you run it more time, so it keep integrating this. So this is the one sample. Every sample is getting incremented in this case. So it depends on the sample time, can be varied according to the need. So the sample time can be fixed for this. So if you take the frequency response of this here, again you can see the slope decreasing slope of the integrator, and the phase which is from here. So this is again it should be from 0 to 0.5 frequency. Okay, hertz here. This depends on, suppose whatever the fs is chosen, depends on that we can locate the frequency. This can be shifted to that particular frequency. And the pole 0 diagram, which is having only one pole at 1. Okay, so this is the pole which is contributing to the integrator. This is pole 0 diagram and the frequency response of magnitude and phase. So we have seen this differencer, integrator, moving averager from the common DSP network. And the Leaky integrator, the next one, has the for this particular generalized transfer function, you have this coefficients a naught is 1 and A1 is 1 minus alpha. Here this alpha is 0.1 has been taken. So, here this is A1, okay, this is A1, and then A2 is made 0, B0 is alpha, okay, 0.1, you can see B1, similarly here B2 here, and then C1 is 0. This part comb filter does not come into picture in this case. So, the leaky integrator has the transfer function alpha, that is B0 is alpha by 1 minus alpha into z power minus 1, where this is 0.1 and this is going to be 0.1 by 1 minus 0.9 z minus 1. So, it is not a, so if you keep alpha 0.01, 0.99, so keep this 1 minus alpha will be 0.99. So, this is the transfer function of the leaky integrator. So, how does it work here? For the given step input, the input which we had used here is this integrator performance. Verify this. It takes so integrator. So, it goes and settles here because of the leaky one. So, this is an integrated performance. The pink one is the y of n here, and this is x of n. So, it is shown continuous, but these are samples. This for every sample it can be plotted as a stem plot as well. So, just for looking at the clarity, it is shown here as a continuous plot, but we can see the output over here, which is having the steps in its discrete one. So, the performance of the leaky integrator is shown in this case. It is also integrating, and if you want to stabilize the certain frequencies which is keep on integrating, in the previous case integrator if you use, if it will explode if, for a particular after certain time period. So, here this could be used to stabilize the integrated value. The response here is what is the leaky integrator do. So, the integrator has the pole which is not on the unit circle, it is slightly pushed inside the unit circle. So, here you can see the 1, it is at 0.9 instead of 1, okay. And the case of the slope, if you take this integrator one, leaky integrator, it is a straight one, and we have this small change in the smoothness of the integrator, and the phase response also having the, which is having here, and as I told you, this is 0.5 and here it will be moving to 0. It is plotted from 0.001. So, here this is the phase characteristics of the leaky integrator. If we look at there is a delay network. So, we can obtain the delay to the signal which is applied at the input. For example, in this case the coefficients have been chosen. A0 is 1, A1 is minus R, whereas R is here as R has a certain it is related to the delay. It's a first order network. So, h of z, what we get from this coefficients a to 0, b to 0. So, these two part will not be coming into picture. A1 and B1 are A1 here minus R, and B1 is 1, B0 is R. So, where R is related to the delay, what we introduce to the signal is minus del delay by plus del delay into 2, plus 2 here. So, which is corresponding for a delay of 0.2, this is going to be R going to be minus 0.091. So, we can fix, depends on the delay, number of sample delays for the signal. So, according to this calculation minus 0.091. So, we have this minus 0.091, and here also R is minus 0.091. So, the coefficients are fixed accordingly, A1 and B0, A1 and B0, remaining this A0 is 1 and R A to B to 0, B1 is 1. Here in this network there is a signal which is given over here. It is a simple sine wave which is of 50 hertz. This blue one is the Xn, and the delay introduced here at least a 1.2 sample, so which is giving the slight delay over here. You can see the delay between the two sequences, okay, the output. So, the delay network which is of first order and second order also, second order, third order, the expression for this would vary. Here the expression for this R would vary for second order and the third order, but here this network will change. So, it's a simple network to form in the delay network to introduce a delay in the input signal. So, this is 50 hertz signal which has 64 samples in it, okay, per cycle. the frequency response and the pole 0 diagram. So we can see that there is a pole and a 0 which is from the transfer function. It looks is outside that we have. Also we have the magnitude response. What we get is this is going to be passing all the frequencies as such. This is 0 dB, and whatever the frequencies between this, it depends on what is the fs. So it would pass at fs by 2. This is fs by 2, and the other side will be from 0 to minus fs by 2, and the phase is like it is going to be introducing a delay, depends on this, the phase which is given over here, phase response. So the delay will be introduced at this portion of here, this phase radians, it is shown in radians. So here the phase characteristics can be seen, which introduces the delay to the signal. So next comes the Goertzel network, in which we have the general transfer function, and then we have the coefficients where h of z, it's from this transfer function. We apply this part will not be coming into picture. There is no co-filter structure in this, but we have the coefficients. A naught is 1, so which comes up to be 1, minus a1 is 2 cos theta. So what is this theta is going to be here? Sorry, theta is going to be 2 pi k by n. The k is the bin index, what we said, this is going to be fundamental, or what k can be fixed there, and this is the theta as well. Here we have the b1, this coefficient, as e power minus j theta. So we have this b1 made as e power minus j theta, j 2 pi k by n, k we have taken as 1, and n is 64 considered for this because of this input signal. The input and then input signal is from signal is having DC fundamental and then second harmonic. So the co-filter coefficients made 0, and 2 cos theta, 2 cos 2 pi k by n, k is 1 here, n is considered to be 64 to extract. So this 2 by n, as you recall from the DFT and the sliding DFT, that 2 by n for kth harmonics factor has been multiplied to get the original signal, original fundamental from this. So this is a Goertzel network which has the poles and zeros in this fashion. Let us see the pole zero diagram of the thing, because before that, so it's a tuned filter which can extract a particular frequency, and the phase shift also is introduced at this point. If we consider the frequency response, this is at 50, so 10, 20, 30, 40, 50, here it is extracting that particular frequency from the rest of the things. Yes, it's the attenuation is good, and if we consider the pole zero diagram, it has this two complex here. Okay, so the pole pair, you can say this denominator constitutes this, and a 0 in the numerator, which is corresponding to the e power minus j theta. So which can extract only this particular frequency. So because this pole is lying on the unit circle, so the output which we get for this x of n, 0.5, 50 and 100, fundamental and second harmonics and DC. So this is the signal, input signal, and the output signal, yes, it is we are extracting this k equal to 1. Yeah, we are getting this 50 hertz from this particular frequency, but the amplitude seems to be growing completely. It's not stabilizing because of this poles on the unit circle. It needs to be stabilized after some time. Okay, so it keeps growing because of this pole on the unit circle, and it's keep accumulating, the amplitude is growing, but it could extract that single tone which is going to be the 50 hertz, and it is eliminating the DC which is present over here, that is 0.5, and then the fundamental is extracted, second harmonic is also eliminated from this. So it can extract only 50 hertz, fine, but the amplitude is not, it should be 1, after some time it should be 1, and stabilizing it. Now the case of the Goertzel, it's giving the peak response. Yes, the pole is cancelling the 0, it gives the peak response, fine, and because of this reason we're not able to stabilize that. So the sliding Goertzel helps in stabilizing this. So in the sliding Goertzel, we have just having the coefficients change b1 and a1 as such, and we have introduced this comb filter part of having n equal to 64, and C1 is 1, so it stabilizes the output. But we can see in the Goertzel as well as sliding Goertzel, we get because of this e power j theta and cos theta, this is going to be a real number, whereas e power minus j theta would result in complex value here. So what we get is x plus jy. So we are trying to get this as a x plus j, real and imaginary over this point. Exactly, the complex number we have got it through real and imaginary, and 2 by 64, 2 by n is multiplied here. So the same thing has also been done in the Goertzel, you can see here, and because we get this as a complex number, and that complex magnitude and angle needs to be converted into real imaginary to get it instantaneous signal plotted. So the output which we have here, this Goertzel network and then sliding Goertzel network, the response now you can see it is getting stabilized, and after n the transient response of n minus 1 up to n minus 1 samples. So at n sample onwards we get the in phase and quadrature component from the sliding Goertzel as network as well. So the real and imaginary parts give this part. Okay. So if we push this poles slightly inside the unit circle, still there will be an issue, in this case a damping factor R, which needs to be done very carefully in this case. Yeah, this is the signal. So we have extracted only the 50 hertz from it. So it can be shifted to any frequency which needs to be done in that case. To eliminate the other frequencies, only the interested analysis frequency can be extracted from this. So the pole 0 diagram of the sliding Goertzel, we have instead of having 0 and 0, one pole get cancelled. So if we introduce this comb filter, then you can see the one which is tuned to 50 hertz here. 1, 10 and here is 50, this is 10 power 2. The scale is adjusted to have this 50 hertz shown in the frequency response. So this is cancelling the 0 at this point, the pole cancelling the 0 and getting the output only the fundamental here, and this is DC will be eliminated, second harmonic will be eliminated, similarly all zeros where it's placed will be eliminated from the input signal. So here we have chosen to show here n is taken 8, whereas in the simulation you used n equal to 64 to show the waveform which has more points. So now the sliding DFT network, this is from the general DSP network, have this R introduced, R e power j theta k, this is A naught, k refers to the bin here, A1, A2, B1, B0 and B1, B2, C1, Rn and 64. So 1 minus R per n, Z per minus n by this. So here we see the pole A naught coefficient which is having this R d per j theta k, that R is used to 1 here anyway, but R can be slightly closer to 1 in the 0.998, so that the poles and the zeros can be pushed inside the unit circle. So this is the transfer function of the SDFT network which we had done already, and the real and imaginary part needs to be separated here because we get this coefficients complex. So the output, the addition of this network here, y of n would be complex. So that is magnitude and phase. So we change to real and imaginary parts separately. So to get and multiply by 2 by n to get this signal here. So this signal is also of the same type which we have used. C1, A1, A2 and B0, B1 are given over here. So the output for this particular signal, it has DC, this is x of n, and the fundamental and the second harmonic. So n is 64 and k we have chosen 2 just to extract second harmonic. You can see this second harmonic extracted in this case. Okay. So after n minus 1 samples, that is the transient response. Either it is going to be any harmonic, there the output can be obtained after n minus 1 samples here. So you have this in phase and quadrature component, that is real and imaginary converted outputs are shown over here. This is giving because this has the second harmonic in this, the signal has second harmonic in it. So n is r is kept as 1, this is fine. It's going, this is y of n for k equal to 2, k equal to 2, that is second harmonic. So when we take the frequency response, this is 1 and then 10 over here, 100 hertz. So you can see the 0, which is zeros DC, 50, this is at fundamental second harmonic. So here we can have this at 0, this will be corresponding to the 0, and the next would be here 100. So 50 will be passed, 10, 20, 30, 40, 50 here. Okay, this is exactly that 50 will be passed, and then second harmonic, third harmonic, and so on. So because we have chosen k equal, this is k equal to 1 case, we have chosen here k equal to 2 to extract only this. In that case, it would cancel the second 0 which is here. So the cancellation will be 0 of this one, k equal to 2 for the case of k equal to 2. This is shown for k equal to 1, okay, so which is cancelling the 0, the pole is cancelling that 0 to extract the fundamental. So to want to extract the second harmonic, if you put k equal to 2, this would show the pole cancelling this particular 0, second one. And n is also 8 for taken as 8 for clarity. And to conclude here, so the total functions what we have seen: moving averager, differencer, integrator, leaky integrator, first order delay network, Goertzel network, and then I have added sliding Goertzel as well, and then the sliding DFT. So here the coefficients are summarized, all the coefficients what we had taken for different cases, and the theta k is 2 pi k by n in this case, and alpha is for the leaky integrator, how small it is, it should be it will perfectly represent the integration. So n can be chosen for the value depends on that application, for cycle which frequency you are interested in and which one to be rejected here. So R is taken 1 in these cases, and delay calculation for delay network is given over here. So with this, we have seen some of the 7 networks at least for the using the general discrete signal processing network. So the using that transfer function of comb filter, recursive part and the non-recursive part, cascading all the 3, and different coefficients, applying different coefficients, different networks can be obtained, and a few more networks I would like to discuss in the next lecture. Thank you.